So we have Professor Holger Maier and Associate Professor Mark Tyre from the University of Adelaide, and they're going to share with us their work on optimising stormwater networks using smart technology and using work that they've been undertaking with their physical rain model to understand runoff rates and how water-sensitive urban design can impact and reduce flood events. So if we think about what Darren said in terms of rainfall and then how we might be managing that, I guess having smart systems that can respond in different scenarios instead of just having, building for the maximum capacity. And then having these types of physical models that we can test our hypothesis against is, I think, is really exciting. So Holger, I will pass over to you. Thank you.
Thanks so much for the opportunity to talk today. So Mark Thayer and I will present on our work on smart stormwater systems. And before I start, I'd also like to acknowledge that I'm also presenting from Ghana land. So I'll start off with just some of the background and the theory, and then Mark will talk about some of the case studies and where we're headed. All right, so we'll start off just briefly outlining, I guess, the journey we've been on. It's sort of been a 7-year journey, and it's been a very exciting journey for us. And there've been a lot of people involved, not just Mark and I, and just lots of honours groups, PhDs, students, other researchers. And I'd just like to acknowledge Jerry Liang and Michael DiMatteo and Graham Dandy, who've also been really instrumental in this work. So I guess in terms of the learnings from this journey, it's been really important for us to learn how to build a pathway from research to practical implementation. And that for us, the big learning was to really listen. So we started off with a workshop in 2017, really trying to understand what the issues are in the stormwater industry. And from that, we could sort of come up with some hopefully clever solutions. But then the other learning there is that it takes trust and also, I guess, investment from industry, because we sort of went from the problem to the idea to some small-scale investment from one of the local governments, to then demonstrating that it might work in practice, to developing our research. And then SMA came on board, and to other councils. We sort of ended up with a bigger scale problem. SMA encouraged us to really think about practical implementation. So that led to a physical prototype, which Mark will talk about. And then more recently, I guess, a funding for a full-scale demonstration site, which I think Rachel will mention in her presentation. So it's been a really good journey. And I think the important thing for us, or one of the exciting things for us, has been the guidance of working with industry. When we're working in teams like that, it's been really great to see the different value different parties can add. We really couldn't have done this without the practical input and the understanding of the systems provided by our industry partners. So that's been really a really great experience for us. And we really do think it's a wonderfully exciting opportunity. As Belinda mentioned in her introduction, and also Darren talked about the uncertainty and what's sort of coming our way potentially, and maybe even in the second half of this year. I think that this sort of work has the potential to be a real game changer, and really we're very excited about the fact that there's been a lot of investment and trust in our work in SA, and so I think we can be a leader in this area. So what are we actually talking about? So smart stormwater systems, storages, what is the motivation? What are they and how do they work? So that's what I'll be talking about. And then, as I said, I'll hand over to Mark, who will give you background on some of the actual case studies we've done and where we're headed. So Belinda mentioned this already in the introduction, but we know that our stormwater systems are stressed. And we also know that things are likely to get worse due to climate change, but also urbanisation and densification, getting more runoff. But as Darren highlighted, there's a lot of uncertainty in what's coming our way. And so we need to be ready. And if systems are already stressed, what do we do about that? And so the traditional solution, which is to upgrade our stormwater pipes, might not work in all situations. And there's a number of disadvantages associated with it. So it's usually expensive, particularly if you've got a big pipe in a main road. It can be easily millions of dollars. But often also it's infeasible just because the road is a contested space. There are lots of other infrastructure there, telecommunications. We're looking at urban greening, so you need the space for the trees and watering them. So there isn't actually sometimes the physical space to put in bigger pipes. Obviously, it's disruptive if you have to dig up a road, particularly if it's a main road, and it's not adaptive or non-resilient. I mean, it's adaptive in the sense that you can keep digging up the road and putting in bigger pipes, or you can over-invest and put in a really big pipe, but it doesn't really have the capacity to respond to those uncertain future conditions that we're likely to experience. And so really that was the problem we were presented with by local government back in 2017. And so the question was, is there an alternative that we can use? And so I guess the solution we've sort of come up with collectively is actually quite simple conceptually, because when you think about what happens in stormwater systems, they're generally uncontrolled. So the water falls in the upper parts of the catchment and sort of rushes downstream, and the flooding usually occurs in the lower lying areas where all the sort of hydrographs from different subcatchments all come in at the same time. So you get these coincident hydrographs that add up to give you the flooding problem. And really, the traditional solution is to really just build a bigger pipe, whereas I guess we're thinking about how can we reduce the flood peak. And the simple answer is if we can socially distance these hydrographs, if we can keep them apart and not arriving in the same place at the same time, we can flatten out the peak, reduce the peak flow. And so the question is really, how do we do that? And the first sort of option is the smart design. And so really the idea is that we put distributed storages throughout the catchment in strategic locations. And that has two effects. One is the attenuation through the storage itself, but really we're looking at quite small storages. So that's not the main factor. The idea is really that if you, again, are smart about where you place the storages and how big they are, you can actually offset the timing of when these hydrographs arrive at the location of interest where the flooding occurs. And obviously having these smaller storages that are distributed has a number of advantages. You don't need a big, you don't need to take up a big space, like big open space for a big storage. It's usually cheaper, it's less disruptive because you've got, it's usually inside streets and things like that. The problem, of course, with that is that there are lots of choices, where, you've got a big catchment, where do you put the storages? How big should they be? How many do you need? And so that's really where the smarts comes in. And so this solution isn't, well, it's adaptive in the sense that you've got lots of smaller storages you can put in place. But of course, it's still an infrastructure option. But by using machine learning, we'll be able to then figure out what the best combination of storages are, where they should be located, how big they should be to try to minimize the peak flow or to achieve the peak flow targets that we're looking for. Now, the nice thing about this machine learning approach is that it's not prescriptive in the sense of telling you this is the solution. It sifts through a large number to really give you I guess, a short list of good solutions, which you could then interrogate. And so there's a feedback loop where we present solutions to industry partners. We look at them, their feasibility, and then we come up with a solution that works for everybody. Now, the good thing about this solution, of course, is it's low tech. And so you don't, it cuts out that sort of uncertainty around, if you're using control, is it going to work? Is it going to fail? So this is really a sort of, low tech solution that is sort of just you put the storage in place, and because of the smart design, it's going to work. The second element is the smart design. And so, the smart control. So really the idea is if you have storage, you can add this control to it that controls the outflow from the storage at the orifice. And that again, value adds or provides another mechanism for attenuating the hydrograph and also offsetting the peaks by delaying outflows and releasing flows at different times. And again, because there's lots of different choices of, when do you control, when do you open the orifice, when do you close it, how long for, by how much. Again, that's where we use machine learning to help with that as well. And so there's another benefits associated with that, not just the peak flow reduction. So from a practical perspective, you can retrofit any storage. It doesn't have to be associated with the smart design. Any storage you've got in the catchment, you can actually add this control to it. It also provides opportunities for adaptation and resilience. For example, the climate change we've heard about from Darren. in the sense of, you can just adjust to the actual conditions. And then, of course, you get the co-benefits of urban greening and water quality improvement by storing the water and not just letting it go out. So just very briefly, when you've got the storage, you can obviously help control flooding with it. Obviously, a simple way of doing it is that's been done reasonably often, is that if you have a forecast of wet weather, you can purge the storage, let all the water go. That gives you the extra storage. But these storages tend to fill up in long duration events. And so we've come up with a way of controlling the storage during the event. And also we've come up with a way that doesn't require forecast of rainfall. You just have to measure the water level in the tank, in the storages, and then the control adapts automatically to make sure that the peak flow is minimized. And you're also controlling storages as a system, not just an individual storage. And then on the flip side, because these events, depending on what sort of AP you're talking about, could be a 10% event. And so most of the time you're not using it for flood control. And then those situations, you can use the water that's stored for water supply and urban greening. So that's my bit done. I'll stop sharing and hand over to Mark, who will talk to you about some of the case studies and where we're going from here.
All right. So thank you very much, Holger. So we're going to talk about some of the case studies we've got where we've aimed to quantify the benefits of smart stormwater storage. Most of these case studies came out of a Stormwater Management Authority project. So I'd just like to acknowledge their contribution. The first catchment is the Trinity Valley catchment. This was performed in collaboration with the City of Norwood, Payneham and St. Peters. This is located on the east of Adelaide, just east of the CBD. This is part of a multi-stage project. I think there was like 3 stages. We were concentrating on the downstream stage, which is called stage 1. And there was a problem in this location at Henry and Laura Streets, which is located here on the map. This is our study area. The general direction of flow is from the right to the left. So there was a really big problem with flooding. These houses would get flooded once every couple of years. The traditional solution that they come up with was a major pipe upgrade. There's already, I think, there's already 2 900 mil pipes in this street. They need to upgrade it to put in 2 1.2 meter pipes in this street. It was going to cost about $6.6 million. There's not much space in these streets, required removal of some of these local trees. It was going to be very difficult to construct because there's limited space, and potentially infeasible due to some pipe surcharging in the area. Now, just upstream of these, on a couple of these Clifton and Dover streets, there were these really wide streets, like with plenty of room for a storage. I think these are about 10 meters wide. There's only one service in there, so there's a lot of room there to put some storage. So the council identified the opportunity to put some storage layouts upstream of Clifton and Dover to see if we could reduce the overland flow on both Henry and Laura streets. So what we did, we worked with the council, went out in the field, identified about 6 potential locations for putting the storages in. We looked at the existing width of streets. We took into account the services, took into account the existing pipes. So this is where we put all the user preferences in. And then we ran the smart design, where we used multi-objective optimization to evaluate. I think we did about 700,000 different layouts because you had 6 storages, each with different outlet sizes and different outlet sizes and the size of the storage and location. There are lots of potential options. And from that, we identified a couple of potential design options. One is given here, where we had 4 600-meter storages located on Clifton Street. Most of the flow actually comes down Clifton Street. and with about 1 meter outlets located in these pipes. Okay. Now, if we compare that to using the size, relative cost, and feasibility, if we compare that to the pipe upgrade, okay, we can see we've got increase in size to existing pipes, cost of 6.6 million, and difficult due to space limitations and tree removal. If we look at this distributed storage approach, we get no increase in the pipes. We have about 2.5 or 2,400 cubic meters of storage. There's plenty of room for these storages in the streets. We estimated the cost was something like $2 million, which is about 66% less. And it's much easier as it's located in these wide streets. You're not going down that really small street. You don't have to worry about trees. It's much easier to do. So that was some of the outcomes from Trinity Valley. The next catchment we looked at was the Pasadena catchment. So this was done with City of Mitcham, with Rachel, who was a great collaborator. So this was City of Mitcham. The Pasadena catchment is located south of Adelaide. The catchment they were interested in is just upstream of the Pasadena Biodiversity Corridor, where the City of Mitcham has done some great work daylighting stormwater to turn underground stormwater into a beautiful urban greening area. So this catchment is located just upstream of the Pasadena Biodiversity Corridor. Now, the problem was that we want to reduce, that was identified by City of Mitcham, was to reduce the peak flow by 16% at the place of interest, which is located downstream here. This catchment is a mix of urban and also it's got some hills face zone up in the upper parts of the catchment. So we evaluated a range of options. We looked at using a traditional end of system storage. We looked at smart design of distributed storages, and we also looked at smart control of the distributed storages. So with the council, we identified 8 potential locations. Rachel and Jerry and I walked around the catchment. 8 potential locations we could do that. We could look at that. We put this through our machine learning and consulted with the council around their user preferences. We again evaluated about 700,000 combinations by running the multi-objective optimization on supercomputer facilities we've got at Adelaide University. And we ended up with a really simple solution, actually, which was really nice. There was 2 locations that were identified. One is on the lower branch of the catchment, and a smaller one was located on the middle branch. We ended up with just focusing on the upper branch because that had the biggest impact as well. So after all these sort of work, we ended up with a really simple solution. And when we looked at the hydrograph, what we're doing here is this is one of the biggest catchments. So we're basically delaying the hydrograph using the storage, and we're doing reducing the coincidence, which is a great example of the concepts that Holger talked about previously. There are 3 branches here, and this is the branch they're actually delaying, and this is one of the biggest catchment areas. So it all sort of matches with some of the concepts that Holger talked about. So we then compared these options in terms of storage size, relative cost, and feasibility. All these options achieved the 16% peak flow reduction, but they varied in terms of their attributes. So if we put an end of system storage here to reduce the peak flow, we've got a storage size of 1,500. This was used as the baseline for the cost, and it was actually very hard to put in a 1,500 storage at the downstream location because there just wasn't the space to do that. In terms of putting distributed storages, we only needed about 600 cubic meters, so achieved the same peak flow reduction with about 60% less size there. The cost was again 60% less because of the because of reduction in size, and it was much easier as it was located in these reserves that are located upstream. So it was far easier to locate these storages than using end of system storage. So we can conclude from both these case studies that distributed storages save space, cost less, and also increase feasibility. We also looked at smart control of distributed storages in the Pasadena catchment. So this graph compares the peak flow reduction for the no storage scenario. These are the passive distributed storages, so just existing storages, and this one is the smart control. If we first look at the minor event, so 10% AEP, we can see that the distributed storage achieves our 16% peak flow reduction. Then when we add smart control to those storages, we can see we get we jump up to around 25% peak flow reduction. So we get a much bigger peak flow reduction if we use smart control. It almost doubles from 15% up to around 26%. So it's a big increase. Now, the distributed storages were designed for the minor event. So that was what happened there. Now, with the major event, so the 1% AEP, we can see that the storages don't really achieve much peak flow reduction. So because they're designed for the minor event, then they don't work so well in the major event, which is quite common. Now, when we add smart control, okay, so all we're doing is adding smart control, we can see we got about a 12% reduction for the major event. So this is quite interesting because you can see that by adding smart control on the existing storages, we're able to achieve a reduction in the major event. So we get much better, the smart control is able to adapt. So the storage size hasn't changed here. All we're adding in is the real-time control. And we also get the opportunity for more water reuse benefits for the Pasadena Biodiversity Corridor. So these events only happen once every 10 years. You have a piece of infrastructure that's sitting there for the other 3,649 days. Okay, so what we do is we use that control to release the water to the Pasadena Biodiversity Corridor. So with no storage, this is the percentage of days that the Pasadena Biodiversity Corridor receives water. With no storage, it receives about 5% of days. With the standard storage control, it goes up to about 7%, so there's a bit of an increase. But when we use smart control, we're able to go up around about 15%. So a really large increase in the water that can be used for that Pasadena Biodiversity Corridor. And that's really exciting for the City of Mitcham because they've invested so much in that biodiversity corridor with the urban greening areas. So that's an exciting opportunity there. Okay, one of the industry influences for this project was a smart stormwater physical prototype, the SMA, where we talked about this project. They said they wanted more than a model. They wanted something we could see and build. So we talked about building a stormwater physical prototype. This is built down in the lab at the university. We've got a controllable storage inflow. So this is a standard rainwater tank that we've got a controllable storage inflow. We've also got a controllable storage outflow. We've got an overflow in case the storage doesn't work. There's a control box that controls both these inflows, the control valves, both the inflows and the outflows. And we've got some flow meters where we can measure the impact. The valves that we're using, oops, just try and get that up. That's not going to work. The valves that we're using basically open and close in response to the flow, and we're able to adapt adapt to the different rainfall events. We're able to generate inflows that are equivalent to a typical lot of about 160 meters squared. We're able to generate, because we can control the inflow, we're able to generate a range of AR&R design storms with different intensities, different temporal patterns. We've got a 2 kiloliter storage, 50mm outlet that's fully controllable. We can test a range of different control strategies. We can do traditional fixed outlet where we just fix this open to a certain size, and we can also assess real-time control. We've also built a floodplain to show impacts. So we've got a floodplain model that shows the impacts. And this is like basically it's like a stepping stone towards field trials. The disadvantage with field trials is that you have to wait for a rainfall event to come to actually test it out. And it's hard to, each rainfall event isn't always the same. So with a physical prototype where we can control the inlets and the outlets, we can do much better way of physically controlling and test out the different control strategies. So we looked at the impact of future climate on peak flows. This was done by a very talented group of honours students last year, where we compared traditional fixed outlet versus smart time real control. The current climate was based on AR&R design storms, 30-minute duration, AEP of 10%. We did an average of 3 temporal patterns. The challenge when you do a physical prototype is that if you do a 30-minute storm, it takes 30 minutes to run. So the students were not keen to run this several hundred times, so they said we'll just do 3 temporal patterns. This is the peak flow outcomes. Okay, from these results, we've got the current climate, which is defined up here. The future climate, which is where we've got a 11% higher intensity, and the another future climate with 20% high rainfall intensity. We tested 2 because of the uncertainty of future climate. So you can see there that with current climate, with the inflow is about 3.8 litres per second, and then the outflow with the traditional fixed outlet and real-time control, it was designed to reduce the flow to achieve our target flow of 1.2, so it all worked quite well in the current climate. When we look at future climate, so we've got this 11% higher rainfall intensity that produced the higher inflow. We get a slightly higher outflow for the traditional and no change for the real-time control. And then when we put in the 22% rainfall intensity, we get a bigger increase in the inflow, and we get a really big increase in the outflow. So we go from 1.2 up to about 2.2. Okay. So with the traditional fixed outlet, we get about a 70% increase in peak flow. Now, the reason it's such a big increase is because the storages are actually become overflowing. Now, with the smart real-time control, we get no change in the peak flow. So smart control is able to adapt to the changes in climate and show that we get no change in peak flow. Now, what's important here is that these are all these results here are measured. They're not from a model, not from a stormwater model. They are measured in that physical prototype. So we've actually run it through and physically undertaken these results. So this is quite an exciting result. It really shows the potential for real-time control to adapt to future climate changes and reduce the need for expensive flood infrastructure upgrades. Okay, one of the other benefits, I'll just take you through this quickly, is we actually use the physical prototype for also undertaking outreach activities. So some of the ideas, what we want to motivate and understand flooding of stormwater management, compare traditional WUSD and smart management strategies. We adapted it for quite a few different audiences. There were middle school, high school students. We're using undergraduate and master's students and also industry professionals. We do have the steps we take is we do some introductory video, and then we do a hands-on design activity. I'll take you through what we do with the design activity. Okay, so what we do for the hands-on design activity, the goal is to stop the houses from flooding. Participants are given a range of different design components. They have some costs. on there, permeable paving, nature strips, and they've got a total budget as a constraint. The participants then build their options in the floodplain model, actually put it in there, trying to achieve their flooding outcomes in the cost. And then we actually test it with real design floods that are generated from the Smart Storm or physical prototype. So we run it through and we test it on, we could do frequent flood events, about a 1 in 10 year, and the students could actually test how their things actually work. That's a smaller flood. And then we can also do, we should actually see how the water is actually flowing through their catchments, what worked, what didn't work. The houses are about 1 to 10 scale, so you get an idea of what's actually working. We could actually look at doing larger, rare flood events, so 1 in 100 flood event. You can see some of the houses have actually moved in this situation, and the students actually they evaluate the effectiveness by measuring the flow, and then they repeat the design process to improve the outcome. The students really enjoyed it. They really enjoyed the hands-on part of it. These are some of the comments. They engaging, fun, hands-on activity, contextualizes real-world constraints and trade-offs, enjoyed seeing outcomes of the floods and changing designs. And one student even said it was the best prac so far. So that's just some of the outcomes from that. Okay, so to sum up, the case studies show smart water saves space, costs less, increases feasibility, adapts to climate change, and provides more water for urban greening. The case studies so far have shown that we showed about a 45% to 60% reduction in space, 30% to 6% reduction in the cost. The technology is available now because it's just putting in storages. The optimization, it's not all fun and games. It does take a bit longer at the design stage because you've got to set up a model and do the optimization. But the extra time at design stage more than pays for itself with the savings during the construction stage. In terms of smart control, we get further peak flow reductions of additional 10 to 20%, significant water reuse benefits, the potential to adapt to future climate change, and it's developed, physical prototype testing has been developed for testing and outreach. In future, we're now working towards a demonstration site, which we've received funding from the Federal Government's Disaster Reduction Fund with the City of Mitcham, and that's what Rachel will talk about. If you'd like to collaborate and be involved in some of the stuff, please let us know because there's some exciting opportunities.
Thank you, Mark. That was brilliant. I can concur with the rave reviews on the physical stormwater model project. I've been in the lab myself and had a bit of a play with the houses on that. So that's a fantastic outcome, I suppose, of the research that you've been doing. And I was also really shocked at having to run 700,000 scenarios. Glad we've got big brain computers that can do that these days, and we don't need to do that ourselves. So thank you. That was brilliant.